All right, so good afternoon, everyone. Welcome to the RMIT Cyber Series seminar series organized by the RMIT Center for Cybersecurity Research and Innovation. Before introducing the center and introducing the speaker today, Malka Halgamuge, I'd like to acknowledge the people of the Waimurang and Bunwurang language group of the Eastern Kulin Nation, on whose unceded land we conduct the business of RMIT University and the lands that I am speaking from today. As we gather virtually across many different parts of the world, we also encourage you to acknowledge the lands in which you are joining us from. We respectfully acknowledge the First Nations people of the 5 Kulin Nations, their ancestors and elders, past, present, and emerging. So next, I'll invite Mark, the director of the center, to give a quick introduction about the center. Mark, please.
Excellent, thank you. It's really just to give a quick overview of the RMIT Centre for Cybersecurity Research Innovation, and the centre that we have here at RMIT is a multidisciplinary centre that draws upon researchers across RMIT University. And what we look at is cybersecurity from an organizational, technology and human perspective. So in terms of these series of seminars and the other seminar series, what we do is have a variety of different speakers from universities, from industry, from government, really talking about cybersecurity from these different viewpoints. Thank you.
Thank you, Mark. All right, so first, my name is Huang, and I'm a member of the center, and also I'm a lecturer in School of Computing Technologies. So today, we have with us Dr. Malka Halgamuge. So Dr. Malka got her PhD in 2007, and she is currently a researcher at University of Melbourne, Department of Electrical and Electronic Engineering. And Dr. Malka has received quite a lot of awards, as you can see in her bio. So I just mentioned a few here, and the noticeable thing is that she didn't just receive awards for her excellent research, but also for her engagement and leadership. So among the awards that she has received, she was recipient of the Chinese Academy of Sciences President's International Fellowship in 2017, Incoming Leaders Fellowship from Australia India Institute at Delhi in 2016. She also received the Early Career Researcher Award from Alexander von Humboldt Foundation in 2013. So today, she'll be talking about the blockchain trilemma. So blockchain trilemma was basically posed by Vitalik Buterin, the co-founder of Ethereum. And it basically says that we can't have 3 for any blockchain system, which is decentralization, security, and scalability. So most systems would just have 2. Clearly, since the time that he raised the issue with the blockchain trilemma, then there have been a number of works claimed to achieve all 3, basically solving the trilemma. But I found that the common theme with blockchain research is that just someone claimed that they solved a problem and someone else say that there's something wrong with the previous one. And okay, so everything is just an ongoing work. And we hope that in this talk, Malka will just show us more aspects and stories along this line of blockchain research. All right, so we have a technical issue with sharing the screen from a MacBook on team on guest. So that's a combination that creates the issue. So let me get back to Malka to see if she's ready with screen sharing, or otherwise I'll just...
Everyone, thank you, Professor Tari, for inviting me to give a technical seminar at the RMIT Center for Cybersecurity Research and Innovation. And thank you, Dr. Han, for organizing this. The title of my talk is Blockchain Trilemma, Decentralization versus Security versus Scalability. Next. This is the outline of my talk. First, I will give you the brief introduction, why this is important, and then I will give you a brief explanation of blockchain technology, and then IOTA Tangle network, blockchain sharding, blockchain trilemma, and smart contracts. And lastly, I will discuss about the security aspects, followed by the conclusion. Next. Society has become hyper-connected in the era of the Industry of 4, the Internet of Things. IoT has increased our need for secure communications. An Australian IoT market was 7.9 billion in 2019 and is projected to rise 25 billion by 2024. During the pandemic, IoT brought new opportunities in remote healthcare, financial transactions, on-demand digital services, and location-aware logistics that are critical to Australian economy. So IoT scalability, with the modest processing capabilities of IoT devices and cybersecurity requirements, have created vulnerabilities that hackers are exploiting. So additionally, IoT devices share their data on various platforms to make crucial real-time decision-making. For example, auto-driving cars or robotic cars. So the privacy of their data and protecting related critical internet infrastructures are essential. So it's essential to adopt blockchain technology to safeguard IoT communities. Next. What is blockchain? Blockchain technology concept was originally described in 1991 by a group of scientists to timestamp digital documents. However, it was first implemented in 2019, Satoshi Nakamoto created a digital cryptocurrency called Bitcoin. Bitcoin is a cryptocurrency and blockchain is the technology that supports it, and they are interconnected theories. Blockchain is essentially a distributed decentralized database that's shared across the networks. The heart of the blockchain is moving from centralized trust to distributed trust or universal trust. So essentially blockchain is an electronic version of paper ledger or collection of transaction or distributed ledger technology that permits data or transactions to be stored globally and securely. In a massive number of computers or servers, we call them as nodes. All these nodes in the blockchain network are contributing to verify and validate transactions. Blockchain allows anybody in the network to see every other person's record in real time, so it provides the transparency. And these blocks are chained together, and this makes the data immutable or immutably linked together, as you can see. Once data or block has been added to a blockchain, it can never be changed again. So it's secure, tamper-proof database or tamper-proof ledger. If a malicious user wants to hack one block, he has to change the entire chain. So once data is entered to a blockchain as a block, it is timestamped and digitally signed as a proof of integrity. A timestamp is proof that the contents of block existed before a specific point in time. Therefore, the information in blocks cannot be backdated. So literally, it would be extremely difficult to change it. So blockchain provides an immutable transaction tracking history. So it provides the traceability. However, still it is anonymous. So blockchain stores data or transaction in distributed ledger that potentially many can access and update securely. So now the obvious question is who has access to this information? Depending on the blockchain type, whether it's a public, private or consortium, we will get access. blockchain is the way to save data and to make it immutable. So key features of blockchain are its decentralization, and it's very transparent, so we can trace who did what and when. And it's anonymous, it's immutable. Blocks immutably linked together. Consensus, it maintains a distributed setting or making rules. So if you have no idea about how blockchain works, I have created 20 minutes video that you could watch. Next. There are some companies who have already integrated blockchains into their services. Bank and finance, supply chain, healthcare, insurance, energy, real estate, government, IoT, and trade. Now I'm going to explain about the IOTA Tangle network. The data structure behind the IOTA Tangle, IOTA is the tangle. It uses directed acyclic graph or DAG, distributed ledger technology, instead of sequential blockchain approach. Main concept behind the IOTA is that nodes issue the transaction in the tangle graph. Sorry, the next slide. Next one. So clients are device layer and issue transaction toward transaction. So the IOTA nodes in node layer. Nodes had read, write, access to IOTA Tangle, and each new node needs to have 2 previously verified transactions to validate new tips according to the cumulative weight to get approval before joining the tangle. So all transactions are connected with Genesis. So this is the structure of the tangle network. So why IOTA Tangle network is more beneficial over sequential blockchain? It minimizes the scalability issues and high transactional fees and performance issues, processing power, memory for conduct mining process, and IOTA is running on lightweight devices with limited power and memory capacity. Next. In this paper, we use IOTA Tangle network. We develop an optimization framework to increase the network scalability and also to provide a priority level of essential transaction in IoT network. So let's consider IoT in a smart city. So priority for autonomous vehicle system or autonomous traffic light system. Data versus data from garbage sensors and automated waste collection. So obviously, we have to give priority for autonomous vehicle system, autonomous traffic light system data to be added to digital ledger as priority. So instead of traditional sequential blockchain, we use IOTA Tangle network for this study. Next. We propose a model to compute newly arrival tips into chosen time frame and estimate the transaction time prior to joining the Tangle network as a new tip. So we propose model to compute newly arrival tips into chosen time frame, and then we estimate the transaction time prior to joining a Tangle network as a new tip. And we develop best tip selection method to enhance the network scalability and to establish the priority level. And we develop multiple objective unconstrained optimization technique for the best approval selection method to make decision that requires a trade-off between network latency with the cumulative weight of the transaction and the approval's effective time after joining the tangle. And we consider to limit very old transaction or potentially malicious transaction to be an approval. So we decrease the network latency and to substantially reduce computation power. Next. As you can see from figure 1, so we compute our model with the tip selection algorithm developed by IOTA Tangle network and few other studies. The proposed model clearly provides a high probability of malicious identification compared with the traditional IOTA Tangle network and also other models. However, if the malicious attacker computation power is extremely high, we observe that increase in the probability malicious identification is insignificant. Figure 2 shows the probability of malicious identification would remain low when the new honest transaction arrival rate or lambda is low. Therefore, IOTA Tangle to be secured, the transaction arrival rate of honest transactions should be large compared to computation power of the attacker. Figure 3 shows the attacker's computation power versus the probability of malicious identification. We vary the ratio of the attacker's computational power and honest transaction arrival speed. And we observe the network to be secured, arrival speed should be higher than attacker's computational power. This is equivalent to the network resiliency or fault tolerance of the IOTA Tangle if the net equivalent ratio higher than, let's say, half, equivalent to proof of work, higher than 1/3, we can consider as a Byzantine fault tolerance algorithm, and 1/4 we can consider as an asynchronous Byzantine agreement protocol, and higher than 1/5 is work equivalent to fast Byzantine PAOX consensus protocols. According to IOTA theory, low-weighted transactions are waiting until weighted transactions complete their processes and high cumulative weighted tips become more robust in the network. However, this is costly as it takes more computational power and increase the network latency. So it's reasonable to assume that depending on the real-time IoT industrial application requirement, a user can make the decision that requires the trade-off between two parameters to limit network latency or decrease malicious transactions while adding a new transaction to a tangle network. Next. So different blockchain frameworks have their own block interval or block time between two blocks. To improve the scalability of the blockchain and IoT integration, it is essential to identify the true block processing time. In this study, we developed a comprehensive model to estimate the computation time required to generate a new block. We consider IoT layer or device layer, cluster head layer, fork edge layer, and cloud layer to adapt fast, real-time, and machine-to-machine communications. Further, we observe the impact by varying data packet size, blockchain type, and encryption algorithm used. Next. We calculated the time component of each and every step in every layer and developed a model to estimate it. Next. Figure A, impact of different blockchain types. We observe blockchain processing time in the IoT network is less than the block interval times of the given blockchain types when the data packet size is below than 200 kilobyte. The difference of blockchain processing time between Ethereum, Litecoin, and Hyperledger Fabric is not significantly varied. Due to the real-time decision-making requirements, the IoT network, it is essential to provide the information and decisions immediately to the end user. So we could not find median block propagation time of all blockchain frameworks. So therefore, the selected blockchain frameworks, it is observed that Hyperledger Fabric is the most time-efficient blockchain type for the IoT network. Figure B shows the impact of different encryption algorithms. We observe that total time is increased from 1.2 to 4.3 seconds based on the selected encryption algorithm type. However, this is not apparent when packet size is less than 200 kilobyte. It is typical, in typical IoT network, the fork layer and cloud layer processes more data volume than the sensor layer. Therefore, the data packet size of each layer should be analyzed prior to incorporate an encryption algorithm in specific layer. So these findings suggest that blockchain processing time, blowfish, and data encryption standard are the time-efficient algorithm for real-time data security in IoT framework. Figure C shows the impact of different layers. In general, layer 3, for which layer assists the reduced network latency of the IoT network by bearing the additional burden from cloud server. In our model, the fog layer has been utilized to perform blockchain consensus processes to minimize the block execution time of the cloud. Typically, block validation process is conducted in the cloud server, and it takes much time because of the higher network latency in the cloud server. So we have proposed to utilize fog layer for that to accelerate block generation process. And figure 4D of D, performance evaluation comparison. Then we have compared our model with similar type of computation model developed by Jiang et al., Liang et al., and Zhao et al. Our analysis identifies potential time-consuming steps when adding a new block to a blockchain, which directly impacts the scalability issues of IoT systems. One potential limitation of this study was the less experimental data we could find on encryption time for different algorithms. Similarly, a median block propagation times of all blockchain frameworks. Next blockchain sharding. Sharding improves the network scalability and transaction throughput of the blockchain networks by splitting transactions into multiple shards or committees. Then transactions in these shards are processed and are validated in parallel. So sharding is most promising on-chain solution for network scalability. Just to clarify, off-chain solutions, they are built on top of the main chain, do not improve the throughput. Instead, move the portion of the transaction off the chain. In contrast, blockchain sharding helps to improve the throughput of the network. Since we have less number of nodes per shard, then the processing transaction decreases the hashing power per shard. So this can compromise the security of the network a little bit. Next. Generally, nodes are distributed among shards randomly. As a consequence, malicious node can be clustered into a single shard, making the entire network fail. To avoid this, we include trust values to minimize malicious nodes or corrupted nodes clustering into a single shard. We propose a penalty factor for a leader selection process to minimize the probability of malicious nodes becoming leaders in the blockchain networks. We improve the trustworthiness of nodes by including the penalty factors and reputation scores to identify the malicious influence towards a blockchain. Next. We consider subjective reputation score based on the neighboring node observation, and behavioral reputation score evaluates the trustworthiness of node concerning different functions, and credit reputation score observing is achieved by nodes other than the neighboring nodes in the network. We observe when penalty factors for subjective, behavior, and credit reputations are increased in all three reputations, the trust scores are decreased. Next. We observe uncorrupted chart probability increases when the number of nodes increases in a chart. The potential reasons for this difference is shard resiliency of adversary model is higher in rapid chain protocol than Elastico and Omniledger. So similar to this, message complexity of single intra-committee consensus is higher than rapid chain protocol than Elastico and Omniledger sharding protocols. Distributing nodes with the same aggregate trustworthiness score, fair distribution among shards could be achieved to reduce the malicious impact into single shards. Next. So there's a clear-cut strategy to support how processors could be incentivized to involve and distribute the committee duties. Participation in committee tasks charges a cost on processors. So rational processors can decide not to participate if their reward is not appropriately given. If each processor within the committee is uniformly rewarded, a rational processor might decide to take a free ride. In other words, get paid without engaging in any committee work. So we design incentive mechanism for sharding-based blockchain network that would apply cooperation among processors by guaranteeing optimal incentive distribution. We implement a fair reward sharding mechanism to maximize the processor's rewards and minimize the computational cost by analyzing the processor's functioning. We model final payout mechanism in a shard based on the total reward mechanism and total mechanism for each processor. We obtain relationship between number of shards and each processor's final payout to maintain network security. Here we consider popular practical Byzantine fault tolerance consensus protocol. Next.
Can I ask a quick question here? So
yes.
Within each shard, then the nodes are already rewarded when they verify blocks, they create blocks, right? So is the fair rewarding mechanism is on top of that, or is replacing that default mechanism?
I don't think I got your question properly. So now yes, could you please repeat it?
Yeah, absolutely. So I think within each shard, so shard operates like a local blockchain, and then within each of these local blockchain, the nodes already get rewarded when they create the new blocks, right?
Correct.
So, so here you're talking about a new fair rewarding mechanism for this node. So is this new mechanism on top of the existing rewarding for block creators, or is it replacing the existing?
It is replacing the existing one.
Replacing, and yes, then you say that it is achieve better fairness.
Correct.
Oh, excellent. So just a quick note, quick remark here that because I cannot see the question coming in the chat. So again, this is interactive. So anyone, if you have questions for Malka, then please just unmute yourself and ask a question. Oh, thanks, Malka.
Yeah, next slide, please. So figure A shows the impact of number of shards in the network in total computation cost. So we observe total computation cost of entire network increases when the number of shards and the computation cost for verifying signatures increases. And figure shows figure B, then here we observe the impact of network size and total number of less powerful processors on total reward distribution. C shows the impact of number of shards in the network on total reward distribution. When the number of shards in a network increases, obviously total number of processors or nodes in each shard decreases because we distribute nodes among shards. So we consider two scenarios. Scenario one, this is a traditional method, processors are equally distributed among shards. And scenario two is the proposed method, processors are not equally distributed among shards. So in contrast, scenario one, scenario two, the fair reward distribution is observed regardless the number of shards in the network. Next. So now I will discuss about the blockchain trilemma. Next. So blockchain trilemma, decentralization, scalability, and security. It is very well-known fact that we can make only 2 out of these 3 at any given time. We call this as a blockchain trilemma. As you can see here, Ethereum and Bitcoin blockchain focuses mainly decentralization and security. Hyperledger and Ripple focuses on scalability and security. Similarly, IOTA Tangle network focus on the decentralization and scalability. On the other hand, decentralization is the key factor of the blockchain. However, if we need the priority of the scalability, then we may have to compromise the decentralization a little bit. So based on this concept, we can pick which blockchain framework suits our organization. We call this as the blockchain trilemma. Next. Before, sorry. So there is no systematic work that analyzes the all properties of blockchain trilemma. So we propose a probability distribution model to analyze all three properties of scalability trilemma. This model considers both transaction processing and failure probabilities. We use hypergeometric distribution and Chebyshev inequality to obtain bounds on probability. We use classical bound Chebyshev for the evaluation of upper bounds of transaction processing and failure probabilities of shards. Next. When comparing transaction probability bounds, there's a significant difference between class A and B protocols. This is due to the resiliency of class B protocols is greater than class A protocols. In figure B, in both classes, the failure probability is decreased when the number of nodes increased in charts. The failure probability bounds of both class A and B have significant difference when only shards have less number of nodes. So class B protocols have a less chance of failing over compared to class A protocols, so have better performance. So when large number of nodes in shard is less, then we have to have more shards in network. There is a higher chance for a network to fail when number of shards increase the network. Then transaction probability in figure C, transaction probability is increased when number of shards increase in the network. However, simultaneously, there's a higher chance for the network to fail when number of shards increased in the network. Then each shard, we have less number of nodes. So potentially, there could be a security issues. These factors explain that scaling up blockchain networks with shards has an impact on the security of the networks. The model is validated with class A OmniLedger, Elastico, Harmony, and Silica protocols and class B rapid chain sharding protocols. We observe that class B protocols have better performance compared to class A protocols. Additionally, regardless of which sharding protocol is being used, sharding only improves the performance of blockchain networks if the number of nodes reduced in a shard or number of shards increased. There are IoT applications like autonomous vehicle system, autonomous traffic light system, where higher security is essential and therefore zero tolerant when they can consider the security level of this system. Therefore, it's important to apply optimal number of nodes for shards to ensure the security levels. On the other hand, IoT application used for agriculture and farming needs the level of security is not crucial. So hence, throughput can be utilized by reducing the number of nodes in shard. Therefore, depending on the requirement, on the real-world application, on the shard size needs to be chosen. This makes the network developers decide on the platform which suits for their application and the users to sacrifice scalability for security and security for scalability when using sharding-based blockchain networks. Next. So now I'm going to explain you about the smart contracts. Smart contracts or self-executing contract where the terms of agreement between a buyer and a seller are directly written as a small program. These are stored in a blockchain. When predetermined terms and conditions are met, it automatically executes. The advantages of smart contracts are most obvious for business collaborations. They are typically used to implement an agreement, so all participants can be assured of the outcome without intermediary third-party involvement. So IoT is the one of the most inspiring smart contract examples, as it is tightly connected with our daily routines such as smart home, smart cars, etc. Next. The aim of this study is to develop smart contracts on public permissionless blockchain to protect the music industry from the consequences of illegal downloading of copyright-protected music files. In our music file sharing platform, where music file owners can upload files and requesters can download music files. We also establish a fair rewarding mechanism for the music industry for the benefit of music file owners, where music files can be traded through smart contracts between music file owners and file requesters. Further, we implement penalty scheme to avoid malicious or illegal music file resources to be added to the community network. Using the proposed architecture for the different blockchains, for example, permission blockchain, such as Hyperledger Fabric or Libra by Facebook, R3 Coda, and new public permissionless blockchain like Byace or Polkadot could be a natural extension for this study. Next. The aim of this study is to develop a lightweight blockchain framework to reduce unnecessary resource wastage, such as electricity due to network traffic and inefficient trading rewarding mechanism during the blockchain mining process, while fairly rewarding concurrent miners. So not only the winner, but also the miners who win but did not get the reward will get minor portion of the reward. This provides miner-driven validation process or a slave agent to approve a new transaction before adding to a blockchain. We improve the reliability of electronic transactions with the consensus of proof of equivalent work. Therefore, all the slave agents connected to master-slave blockchain equally get the chance to engage in a validation process as miners. Here we consider total number of mining transactions performed by the successful miner who failed as a successful rewarder to overcome his computational and networking cost. We analyze the complexity and feasibility of the proposed model by investigating significant weight percentage and the impact of two variables, time taken to identify the nonce and the rewarder success rate history. Additionally, we adapt an adversary model to obtain the fraction of participating masternodes and slave agents that need to be compromised by the adversaries to compromise master-slave blockchain. In this study, we consider a scenario of applying master-slave blockchain in electronic healthcare system. Next. We adopt permission blockchain framework to enable IoT device access control, primarily to protect cyber infrastructure of the IoT networks. For example, cloud, fog, web servers, application servers, routers, switches, gateways, remote sensors, computers, controllers, actuators, everything, including storage, including computing grid and data grid. So we consider this as the cyber infrastructure. There are some existing weaknesses in public key infrastructure system to IoT networks. It is challenging for IoT device owners to maintain IoT device certificates. and devices' secret keys are installed in a device itself instead of real owners. So manufacturers may expose to secret keys. And private key of a single root certificate authority can be stolen by an adversary. Either periodically or on demand, list of the IoT devices root certificates should be updated. Finally, online certificate status protocol responders are essentially unsafe for DDoS attacks. Hence, it's apparent that decentralized public key infrastructure system to IoT networks addresses a centralized system's weaknesses. So we consider the different blockchain in a different domain or different IoT networks. We consider the IoT network with n number of devices and s number of security access administrators. The security access administrators work as the certificate authority, CS, in traditional centralized system and authorize access queries in decentralized fashion. We cluster nodes into a different domain or various IoT subsystems. Next. We derive latency model including communication latency, digest computation latency, message authentication code, computation latency, and latency for device access query via security access administrators, and latency for authorization and device access, and latency for adding a transaction to blockchain. Next. Figure A, a message size in bytes. B versus a latency for critical infrastructure access control. That the latency for infrastructure access control increases when the message size in bytes increases. As expected, time taken for communication is the highest. The increment shown to be slightly significant in latency for device access after permission granted by the security access administrators. In figure B, for the same message size in bytes, we observe the latency with our proposed model is higher than the Ma et al. 2019 model, 75.5%. So Ma et al. Model underestimated the computation time for this case. Our proposed model could be utilized to estimate accurate time to securely access a target object using blockchain, to observe the scalability performance of the network, and to detect malicious network activity by observing if unusual time exists. Next. This is the last study I'm going to explain. We developed a probabilistic model to analyze malicious attackers' success probabilities on a blockchain-based 8 different types of cyber attacks. We consider broader gateway protocol, hijack attack, selfish mining attack, distributed denial of service attack or DDoS attack, Sybil attack, block withholding attack, eclipse attack, identity revealing attack, and domain name system attack. We then analyze attackers' success probabilities based on blockchain resiliency or fault tolerance provided by the consensus algorithm and network size, network vulnerability factors of the cyber attacks, and the locations where attacks are unsafe in the blockchain network. We utilize the proposed model to analyze the impact of the network vulnerability factor based on all 8 attacks. Next. We compare malicious attackers' success probability values with a few consensus algorithms such as proof of work, Byzantine fault tolerance, fast Byzantine PAOX, and asynchronous Byzantine agreement. We use these 4 consensus algorithms as they have different network resiliency value to us to compare. All attacks seems more sensitive to the Byzantine fault tolerance algorithm than proof of work, those 2 major algorithms. Perhaps this connection maintains the blockchain trilemma idea that no digital ledger in public blockchain can fulfill all three elements: scalability, security, and decentralization simultaneously. In all scenarios, we simulate by varying the number of nodes in the network. We observe that successful attack probability decreases with the number of nodes. The hijack attack, BGP hijacking attack, and DNS attack demonstrate negligible malicious attacks, especially when the larger networks number of nodes is greater than 80. However, this decrement is observed as insignificant for other attacks like DDoS, BWH, Eclipse, identity revealing, selfish mining, and Sybil attacks when number of nodes are greater than 1000 nodes. Next. There are a few locations where malicious users can deploy an attack to tamper data in a blockchain network. Hence, in this analysis, we consider malicious attacks sender node and transmission or communication links, and control site or servers or databases, or malicious attacks on receiver end, actuators, edge devices, or maybe smart contracts. When considering the location of attacks, our results show that sender and receiver nodes are more vulnerable than control site and communication or transmission links in blockchain networks. Next. Our results show that malicious attacker success probabilities in DDoS attack or BWH and Eclipse attacks are slightly higher than other attacks in blockchain networks. Next. This figure shows that the network exposure factor, X, we consider, can create potential impact on the malicious attacker's success probability based on the type of the attack. This value could change based on how critical the given network is exposed to cyber attacks. Therefore, this is obviously network-specific choice. For example, a blockchain network related to banking sector obtains higher exposure factor than the blockchain network related to agriculture sector. It should be noted that the X range that used by Liang et al. Adapted in this study is relatively high, indicating that the blockchain network is highly exposed to cyber attacks. So essentially, we considered almost the worst case scenario in our simulation. However, in reality, this may not be the case. Next. So this is the conclusion of my talk. Blockchain technology has potential to adapt into almost every industry, including the Internet of Things, for industrial automation, farming, supply chain, multimedia industry, banking, health sector, identity or device management, asset tracking, information technology, infrastructure protection, or cybersecurity. Blockchain have a natural scalability issues of dealing with massive data communicated from IoT networks. And these decentralized networks introduce communication processing overheads that need a lot of computing resources. And still, cyber attacks continuously use internet to spread malware. Such attacks can expose vulnerabilities in service systems and other IoT critical infrastructure to gain unauthorized access to confidential data and information while making them unavailable to authorized users. And software application security is also an essential aspect of IT infrastructure. So these incidents highlight the demand for enhanced security protection for IoT network infrastructure. Additionally, lack of interoperability between large number of blockchain networks with different consensus mechanism, different security measures, and different programming languages even. In sharding, overuse the single priority shard during cross-shard transaction could be a problem too. And the other potential solution, vertical scaling, adding more resources, disk, space, storage, and communication bandwidth, and computation processing capability to each node, and horizontal scaling, adding more nodes to the network, and reduce communication and computation overheads, and adapt malware update system using smart contracts. Next. I'm not a blockchain expert. Still, I'm learning many things in this space. So thank you all. Any question?
Thanks so much, Malka. And the talk is very interesting and cover a wide spread of different topics in blockchain. As you can see here, from starting security, scalability trade-off to fairness, to latency, to attacker success probability. So I think that's a great amount of work. So any question for Malka? So you can just unmute yourself and ask Malka directly. Let me stop sharing here. So while waiting for questions from the audience, and I'm just curious about the case of using smart contract for music industry. So suppose you have a blockchain and every music producer would just upload the music to that blockchain and managed by the downloads and upload managed by the blockchain. Then is it possible that people can still, let's say, buy the download the songs from their blockchain and then upload to the normal internet, and still they can still do the pirating? So I'm wondering if that is the case.
It depends on which sort of blockchain you are using, private blockchain or public blockchain. If it is a public blockchain, we need to consider the everyone can use, is like Bitcoin. So if it is a private blockchain, so it's depend on whether you are part of that blockchain. So then, yes. Then if it is the case, then you can upload. But again, it's between the requester and the music composer. We consider all those things. So based on that, you can make the contract between them.
I see. And probably you can use something like watermarking to track, right? So who is the guy who upload the material to some forum online, something like that.
Yeah.
I see. Interesting. Okay, so any question here?
Hi, Malka. This is Calvin Decudo. Do you mind if I ask a question?
Yeah. Any question?
Thank you. I'm sort of trying to determine how best I ask this question. It's related to one, implementation time and implementation cost, and obviously part of the answer will be determined by the scope of how we actually implement blockchain. But in reality, if we look at other organizations, do we have live examples of where it has been implemented and how long it's taken and what it's cost, and obviously the success element out of that?
Yeah, very good question. In fact, honestly, I do not have the answer for that question because I have not implemented real blockchain. So most are mathematical model and simulation. Yeah, sorry. Therefore, I don't know exact actually timing. But what I did was I used some experimental data for my simulation.
Thank you.
There's also a question from Nicholas Huppert as well. So Nicholas, can you unmute yourself and ask Malka directly? All right, what he asked there is, okay, no mic. The answer was given anyway, thanks. Okay, so you already answered him his question basically. Okay, thanks Nick. Any additional question for the speaker? So can I ask one more question on
Yeah, sure.
the rate, the trustworthiness, right? I think of the other notes, I think at the beginning of your talk. So how, like, who would be the one who rate, or everyone rates everyone else?
Yes, everyone else. Yes, everyone get the opportunity to vote.
I see. And so do they do it independently, or do they rely on, say, neighbors rating as well? Or
So it's depend on yes, for the study what we did, we consider that rating as well, but in general, so for the blockchain network, so everyone get the equal opportunity. If it depend on you are in the full node or the partial node, that means you just receive, or you have enough computation power. If you have enough computation, so you are part of the network and you can vote. But in the study what we developed, so there we consider to reduce the malicious attacks. So then we consider, so we give the rating for the neighboring as well. So that means we consider we know each other, right? So if we to identify that, to reduce the malicious users. So if you don't know, if any stranger comes, then they don't get the marks from us. So that will reduce him to get the opportunity. So therefore, I won't get the opportunity to join the network. So that's why we propose this rating system based on that reputation scores. We give the scores.
So everyone has different scores about everyone else, and it's not a common voted common let's say board of trustworthiness for everyone. So because I was thinking in the way, like, if you trust, let's say if you trust your neighbor, then maybe you can use his rating to a certain influence on your rating as well, like the Google case, ranking the website. Like if you are pointed to by a very famous website, then you are most likely also very famous, something like that.
True, but this is there are 3 different scores. So also you get the history of we consider their history, the history of whether he has done the malicious activities or not. We consider that part as well. So there are 3 different parts we are looking, not only the neighboring scores. And also we consider the everyone's as well. So one is the neighboring, other one is everyone, and also we consider the history as well.
I see. Okay, actually,
so we can in fact we can improve that to get more restrict and more real scenario to restrict malicious users.
I see. I think I do have to look into your paper to get all the details. It sounds very interesting to me. So any last question for Malka before we end the session? All right. So I think I'll share. Do you mind if I share the slides in here? In this chat? Okay. Sure. I think probably people want to follow up with, because there are quite a number of papers you mentioned in there and the results. Again, so thanks a lot, Malka, for coming and sharing your work with us. And thanks to everyone for coming. So we'll have this technical seminar around once a month. So we'll announce the next one very soon. So again, thanks, Malka. Thanks everyone for coming. And
thank you. Thank you for giving me. Yeah, thank you for giving me opportunity to give a talk in the Center of Cybersecurity Research and Innovation. Thanks so much, Ron, for organizing this.
Thank you, everyone. Have a nice weekend. Bye.
See you.